Good morning. Let's begin lecture 22. We pick up from the last lecture where we talked about the two-channel filter bank, alias-free filter bank, and today we will continue on that discussion. I'd like to cover some aspects of how do we eliminate amplitude distortion, how will we eliminate phase distortion. We will also look at how the historical development happened, which came first, how did people actually solve this problem of removing all three forms of distortion. As I mentioned in the last class, the tools that we have developed in the material covered so far, one of them is polyphase decomposition. We just want to know whether polyphase decomposition is going to give us any insights into the tools or the solution that would eventually be able to satisfy all of these three, removal of all three types of distortion. We also know that we have linear phase filters, and the use of linear phase filters removes phase distortion. So again, we will explore both of those in today's lecture and then see how we can leverage these results for our purpose. So the framework is the two-channel maximally decimated filter bank. Again, the term maximally decimated means that your total sample rate, number of samples per second after the splitting into the sub signals, sub channel signals, should be the same as the input rate, sampling rate, sample rate. So you can see that both of these are downsampling by a factor of 2. So therefore you would have the same input and output sampling rate. Now we showed for this case that the output reconstructed signal or the recombined signal to be equal to a transfer function which we can write as T of Z. T of Z is the signal transfer function, and the next one is the aliasing transfer function, A of Z. Now if A of Z is set to 0, then we get alias free condition, and that is something that we had already looked at, because there was one choice of transfer or the choice of filters that showed that the aliasing can be cancelled. And again, this is something that I am sure you can try out. Now if we have succeeded in setting A of Z equal to 0, then we can now start focusing on the transfer function. So if A of Z is equal to 0, then we focus on the transfer function T of Z and say that like any other transfer function, it has got a magnitude response, it has got a phase response, and the magnitude distortion, if you want to eliminate it, the magnitude response must be a constant, which basically says it must be an all pass filter. Phase distortion says that this transfer function must have linear phase, and therefore in that condition then we would be able to eliminate the phase distortion as well. We did spend a fair amount of time going through the drawing how if the green line was the input signal, H0 and H1 were the two filters that were available to us. Then we went through and showed that the aliasing terms, which come from the two terms that are in the aliasing transfer function, basically give you some non-zero value around pi by 2 and around 3 pi by 2, and similarly the other transfer function, other component also has got the same. And looking at the spectral occupancy, if these have more or less the same magnitude response and opposite phase, they would cancel each other, and that is what is the underlying principle. Okay. So some elements that I just wanted to emphasize on. So we can get rid of the aliasing, that is point number 1. And the choice of the filters that will eliminate aliasing, one of the options is here. This may or may not be the only option. So this is a sufficient condition for the elimination of aliasing. And when we eliminate aliasing, we get a transfer function LTI system, and we can take care of the magnitude response and phase response. Now I'd like to spend a few minutes on this transfer function, because I think it's a very important element in our development of the theory of the filter banks. So x hat of z is equal to T of z times x of z plus A of z times x of minus z. Right? That's an input output relationship for the two channel maximally decimated filter bank. Okay. Now supposing we had the following, that T of z corresponded to an impulse response T of n. Basically let us say that the time domain representation of the transfer function is characterized by an impulse response, and in the same way A of n was the inverse z transform of the transfer function A of z. supposing these existed. Okay. And now I would like you to write down the time domain equation for this. X hat of n will be t of z x of z, that means it will be a convolution of t of n with x of n. This part is straightforward. T of n convolved with x of n, okay, my x, okay, hopefully that does not look like a star also, okay. This is x of n, okay. Second term, please tell me what this is. A of n convolved with minus 1 raised to the power n x of n, correct? Okay, good, very good. So now please help me write the actual convolution sums. This is summation over k going from minus infinity to infinity, t of k x of n minus k plus it will be a of k minus 1 power n minus k, correct, because I have x of n minus k, and this will be x of n minus k. Okay. So, I am going to split this in the following form: minus 1 power n minus 1 power k, minus 1 power minus k is the same as minus 1 power k. So, that is the thing. So, this I am going to now do a combining of terms. It is going to be t of k plus minus 1 power n, okay, minus 1 power n minus 1 power k a of k, this whole thing into x of n minus k. Probably wondering where this is heading towards. I think the insight is going to come in just the next line. So, let me take the case of n even. In that case, I can write down a new sequence g of n, g0 of n, which is defined as, since n is even, it will be t of k minus 1 raised to the power n is plus 1 plus or plus minus 1 raised to the power k a of k. Similarly, for n odd, we will get another sequence g1 of n is summation t of k minus 1 power k a of k. Okay. So, if n even, n odd, we get different sequences. So, we can now combine these results into a very insightful result, which says x hat of n can be written to be summation k from minus infinity to infinity, g0 of k g0 of k x of n minus k if n is even, it is equal to summation over k g1 of n x of n minus k if n is odd. Do you agree with that? Basically, you get a different sequence when you are dealing with time n is even and the time when n is odd. Sorry, this is g naught of k, I am sorry, absolutely correct, yeah, this is g naught of k. Okay. So, in other words, I am very glad you brought it up, because for n equal to even, n is even, we have to look at the impulse response being g naught of n, and n odd we have to look at another impulse response, and so the representation of this comes out to be the following. I have two filters, g naught of z, which corresponds to the transfer function of g naught of n, second filter g1, which corresponds to the g1 of n impulse response, g1 of z, both of them producing the output, and it is as if the output sequence kind of goes back and forth. if it is and it chooses the upper branch if n is even, chooses the lower branch if n is odd, and this is x hat of n. Okay. So, I have not done anything about alias cancellation. I have just let aliasing be there, and I have analyzed what is my input output relationship. Okay. Now, here is the key summary statement. Is my overall system linear? Input and output a linear relationship? Yes, whether its time is even or odd, linearity will satisfy. Okay. So, linearity you can put a tick mark. Okay. Is it okay? The second one is that is it time invariant? No, it is time varying. So, that also you can tick off. Time varying. Okay. There is one more element which is important in the time varying aspect. See, time varying just says that every instant of time it is a different impulse response, but this one does not have a different impulse response for every instant of time, it is actually a periodic variation. So, this has also a third element, which is that it is the impulse response is periodic. Okay. So, that also is part of the description. So, this input output 2 channel system where we talked about a maximally decimated system has the following, it is described in the following way: it is linear, it is periodic and time varying. See, we were used to LTI, linear time invariant, but now this is 3 components. This is linear, periodic and time varying. Okay. Okay. So, that is what it is, and this is insightful for us, because even if you go to an M channel system, you can visualize it as, yes, it is linear, it is going to be time varying, but it is not arbitrarily time varying, it has got a periodic structure to it, which once you know that there is some structure to it, we can always exploit. That is the whole premise of signal processing, that once you detect a certain structure in your signal, you can then take advantage of that. So, a lot of the theory behind this says, okay, now we move from LTI systems to a broader class of systems which are linear time varying systems, but they are not arbitrarily varying, but they are periodically varying, and that is a very interesting and useful class of systems. Again, as opportunity comes, you will have an opportunity to work with that. Okay. So, now we go back to our original plan of cancelling aliasing, removing all of the things that are unwanted. So, that is our focus for the rest of the lecture. Now, aliasing cancellation, let us go back and summarize whatever we know about aliasing cancellation. Aliasing cancellation says that we have to choose the filters in the following manner: choice of filters f naught of z equal to h1 of minus z, f1 of z equal to minus h naught of minus z. Okay. So, these were the 2 conditions that were required to be satisfied. This is an important condition. And if you know, and if you want to just sort of keep a reference, the overall equation is x naught of z is equal to t of z times x of z plus a of z times x of minus z. So, let me call this as equation 1, this is equation 2. Now, there is one more element that sort of became apparent to us from our discussion when we were doing the graphical representation. That was the following: in order for us to have minimum amount of aliasing, that means the h naught of z could have been like this, but in that case, if this is h naught, then h1 would have to be much wider, because if you remember, we said that you cannot have any portion of the spectrum that is not covered by either of the filters, because you must preserve the information. So, this would have to become h1. then the lower branch will have a lot of aliasing. So, which means that that is undesirable. So, obviously, when you say that okay, minimize the aliasing, but you must also prevent that there is no there must be full preservation of the signal, then you say that okay, H naught must have a passband edge which is close to pi by 2, must be close to pi by 2. So, if that is pi by 2, because then you would have minimum amount of aliasing, then the other filter would also look like this, because that is those are the relationships between these two filters. Okay. So, what we observe through intuition is that this is pi, okay, and if you want to draw the full form, this would be all the way to 3 pi by 2, and then the other image of H naught would also show up. Okay. So, this is 3 pi by 2 and here we have 2 pi. Okay. So, this is the, so obviously this is not a desirable form, this would be the desirable way. You would like to have the filters crossover at a convenient point. Now, this was obviously observed very early in the study of filter banks. So, the first reference comes in 1976, I think I may have mentioned the name already, it was by Quadrature, and he said that yes, the filters must cross over around pi by 2, and he went on to say that there are certain advantages if these are not arbitrarily chosen, but since they have to have a certain symmetry around them, he said why not introduce them to be actually shifted versions of each other. Okay. So, if this is pi by 2, this is pi, okay, I am drawing only from 0 to pi. The observation that he suggested was the following. The observation was why not choose H1 of z to be equal to H naught of minus z. Now, does that in any way limit us in terms of the generality of the solution or constraints? Now, why would you want to do that? This one means that you have to design only one filter, because only in the other case you have to design H naught and H1. Now, you would design, now let us just sort of go back and plug in and see what does this. So, by the way, pi by 2 has got a name, it is called the quadrature frequency. Quadrature frequency, because it is 1/4 of the sampling frequency, quadrature frequency. And now, if you actually think of a mirror at the quadrature frequency, H naught and H1 are actually mirror images of each other, because that is what happens when you design one to be the other, and they are satisfying this condition. So, this quadrature symmetry, so this basically along with the other conditions enforce a quadrature symmetry, and this class of filters, when you have two filters which satisfy quadrature symmetry, came to be called as quadrature mirror filters. Okay. So, quadrature mirror filters, and again the historical development was from a angle of let me get rid of aliasing, let me simplify the filter design, and so the symmetry came about, and so this actually came to be used very widely, quadrature mirror filters. And if you look at any of the filter bank literature, you will see this acronym QMF, and you know where it exactly comes from. Quadrature mirror filters started from two channels where you have a certain symmetry around the quadrature frequency, and of course the aliasing cancellation constraint as well. So, now if you combine equation 1, okay, and you have, this is now equation 3. So, 1 plus 2 comma 3, add, I want to get rid of aliasing with this constraint, please substitute, you can verify that T of z, the transfer function, will come out to be 1/2 of H naught squared of z minus H1 squared of z. Okay. And H1 squared is H1 of z is H naught of minus, so this can also be written as 1/2 of h naught squared of z minus h naught squared of minus z. So, this is a observation that came from introducing the quadrature mirror filters. So, if I design it to be a quadrature mirror filter to begin with and choose the synthesis filters according to equation 2, then I get a form that tells me that the overall transfer function now depends only on h naught, because h 1 and h naught are related to each other, f naught and f 1 are related to h 1, h naught and h 1, and therefore, ultimately you have written the entire expression in terms of h naught. Now, the goal is that I have to design h naught, but ultimately what do I need to, what would I like to satisfy? I would like to satisfy T of z to be equal to T e of z. I would like it to be all pass and linear phase or something close to that, okay. All pass and linear phase is a contradiction, you cannot satisfy both of those in the same except for trivial cases. If you take a delay, it would satisfy, right. So, but all pass and linear, so why would I want all pass? Because I want to get rid of magnitude distortion. So, eliminate magnitude distortion, and the linear phase is to eliminate phase distortion. Okay, so that is what, and again it has given us a expression, but really has not told us how to solve this problem. Okay, so this is where we are. So we said, okay, from now on we will work only with QMF situation, because that has simplified our problem to one level, but how do I get the solutions that are useful for us in terms of the design of the filters. So we go back to the tools that we have already developed, polyphase decomposition, and ask if this was going to give us any insights in terms of the design of the 2-channel filter bank. Okay, and probably in the course of this discussion you also get a feel for that this is a somewhat of a involved problem. It is not a trivial problem, it is not something that we can solve straight away. We have to basically plug along, and you will see that there is a fair amount of effort and attempt to actually solve this particular problem. So h naught of z, h naught of z, I am going to downsample by 2, so 2 polyphase decomposition, 2 channel polyphase decomposition, E naught of z squared plus z inverse E1 of z squared. Okay. Now the QMF condition says h1 of z will be equal to h naught of minus z. So that gives us a fairly interesting polyphase decomposition. It is not a new polyphase decomposition, it is actually the same as before with only a minus sign, minus z inverse E1 of z squared, and that is because of the symmetry and the shift that has happened. Okay. Now combining these two equations, we can write down the analysis filter bank h naught of 1, h1 of h naught of z in the following way: 1, 1, 1, minus 1, and the polyphase components E naught of z squared, z inverse E1 of z squared. Okay. So that is equation 4 if you wish to write it down. Okay. Now I want you to write down for me the synthesis filters. So very quickly let us just pencil them down and then write it in matrix form. F naught of z from aliasing cancellation principle choice, h1 of minus z. So that is straightforward. h1 of minus z is actually equal to h naught of z. So f naught and h naught and f naught actually are one and the same filter, because of the polyphase decomposition, the QMF constraint, they actually map back to the original one. f1 of z, f1 of z is minus h naught of minus z. This is the same as minus h1 of z. h1 of z we already have written down. So this will be equal to z inverse E1 of z squared minus E naught of z squared. Okay, that is f1. Okay. Please follow along. If I have made any sign mistakes or something, just flag it down immediately. Okay. So, combining these two equations, I would now like to write down the synthesis filters. Remember I told you analysis filters always written as a column vector, synthesis filters always written as a row vector. The reason is you would combine it with a column vector to produce a single combined signal. Okay, so this is F1, okay, F naught of Z, F1 of Z. So, it is written as a column vector. Let us write down the expressions. So, we would now write it down in the following way. F naught and F1, if you look at it, it has got two polyphase components. I am going to write it in the following manner: Z inverse E1 of Z squared and E naught of Z squared. I will explain in a minute why I have chosen this. If you write it in this form, notice that the matrix that does the combining of the polyphase components comes out to be 1 1 1 minus 1. Okay. And that is a orthogonal matrix. So, I like to preserve that because that was there in the analysis filters. I want to retain it in the synthesis filters as well. Now, the reason for doing this also highlights one point that we had mentioned earlier. We said that, remember that this is type 1 polyphase, this is type 1 polyphase decomposition, type 1. What was the type 2 polyphase decomposition? What would it have been? It would have been Z inverse R naught of Z squared plus R1 of Z squared, right. The delays are basically the delays are in a different order as in the type 1. So, this is type 2 polyphase decomposition. If you go back and look at your notations, again we do not use it too often. So, we did not specify too much, which basically means that this is been labeled as R naught of Z squared and this has been labeled, did I get that correct? Yes, and this has been labeled as R1 of Z squared. Okay. So, basically if I do that correctly, yes, yeah, so I get the correct representation. Okay. So, now the key element for us is to use this in interpretation. So, what I would like to do is redraw the figure for you. So, the 2 channel polyphase decomposition can be 2 channel maximally decimated filter bank with polyphase decomposition can be drawn in the following manner: E naught of Z squared, E naught of Z squared, Z inverse E1 of Z squared, E1 of Z squared. Now comes the 2 by 2 DFT butterfly, okay, basically the crisscross operation. The lower branch comes with a -1, these all the arrows moving to the right. The lower branch alone comes with a multiplication of -1, okay, outputs, and here you would have the downsampling by a factor of 2. Downsampling by a factor of 2. Okay. Now, on the other side, it would be upsampling by a factor of 2, followed by the synthesis filters. The synthesis filters, if you look at the implementation, also have a crisscross butterfly, the same structure, all lines moving to the right, the lower branch having a multiplication factor of -1, upper branch is R naught of Z squared. Keep in mind this is the same as E1 of Z squared. The lower branch is R1 of Z squared, R1 of Z squared and then combined with a delay element Z inverse added together, output, all the arrows moving to the right, and this is x hat of Z, and this is the same as E naught of Z squared. Okay. These are equal. Okay. So, this is the overall structure that we have obtained. Okay. Now, what you could do is move the downsamplers and the upsamplers and get a certain amount of insight. What you will find is that these two matrices will cancel each other because they are orthogonal matrices, and of course, it will give you a diagonal element or diagonal, it will basically become a scale factor of 2, because when you multiply these two you get only diagonal elements with elements equal to 2. So, you will get a multiplication factor of 2, upper branch will be E naught of Z, on this side it will be E1 of Z, this one will be E1 of Z, this one will be E naught of Z. Okay. So, you look at both of them and you say that, well, what did I get at the output is something very interesting. Upper branch and the lower branch give me the same thing, and of course, there is the demultiplexing and the multiplexing. Now, well, that still puts you in a multi-rate environment. So, you say, okay, well, wait, that is okay, that is good insight, but let me just go back and say that under this condition, if we went back to our original equation, the original equation, if you recall, said that T of Z, what was it equal to? H naught of Z F naught of Z plus H1 of Z F1 of Z. We are guaranteed that aliasing is cancelled here, right. So, why worry with this downsampling, upsampling? So, I want to sort of work with the non multirate framework where they say, okay, T of Z is this. So, this can be written as F naught of Z F1 of Z, the synthesis filters, as a row vector with H naught of Z H1 of Z as the column vector. And if you now write down the expressions, what you will get is 1/2 Z inverse E1 of Z squared E naught of Z squared, a 2 by 2 matrix 1 1 1 1 1 minus 1, followed by another 2 by 2 matrix 1 1 1 1 minus 1, and this one would be E naught of Z squared Z inverse E1 of Z squared. Okay. Now, these two is what I mentioned, they will cancel each other, you will get 2 0 0 2. It is like an identity matrix, but with a scale factor of 2. So, that scale factor will cancel off the scale factor of 1/2 that is sitting outside. So, what you will eventually get is the following, you will get Z inverse E naught of Z squared E1 of Z squared. Now, which was the same insight that you got from the multirate structure as well. Basically, you know, once you move the multirate blocks, then the upsamplers and downsamplers, the two matrices will cancel, and then upper transfer function, lower transfer function come out to be the same, and that is exactly what we got, and this is equal to T of Z. So, T of Z comes out to be the product of the two polyphase components. Okay, and given once you know H naught, you can get E naught and E1. Okay. Now, has this given us any further insight? First and foremost, does this hold for all cases? Yes, this result holds for all cases which satisfy the following. Basically, they must satisfy the QMF condition, H1 of Z equal to H naught of minus Z, that is the QMF condition, and then the aliasing cancellation is F naught of Z is equal to H1 of minus Z, F1 of Z equal to minus H naught of minus Z, This is the AC, AC stands for aliasing cancellation. Now if I satisfy these two and then combine it with polyphase decomposition, then aliasing is cancelled and I get my transfer function T of Z given by this expression. Okay. T of Z is H is half H naught. Okay. So F naught, no, but I still have a problem, no? I still have, so there is a 1/2 here, which is the 1/2 that has shown up here. Let me just put a question mark here, is this 2 there or not? It's a scale factor, so but nevertheless we need to be careful and consistent with our expression. So yeah, so I'll double check it from the beginning, but for now, so this is the transfer function with the QMF condition satisfied, the aliasing cancellation condition satisfied, and the polyphase decomposition being applied. Most important in any result is the interpretation and the insight that you get from there. So the transfer function being T of Z being equal to, let me write it with the scale factor for now, 2 times Z inverse E naught of Z squared E1 of Z squared. Now I want to eliminate magnitude distortion, phase distortion, and see if how I can satisfy those conditions. So in order for the phase distortion to be eliminated, or first of all amplitude distortion to be eliminated, if I want to eliminate amplitude distortion can be eliminated only under one condition. E naught and E1 both are transfer functions, both of them should not have any amplitude distortion. So which means that these will have to be delays. E naught of Z, E1 of Z must be delays. I will call this as some C naught times Z power minus N1 E1 of Z C1 Z power minus this is N naught and this is N1. Okay, some two different delays. That is only a condition under which they will have. So now you may say, well, can they cancel each other? Yes, there are certain tricky constraints, but remember E naught and E1 do not have a relationship, you cannot really constrain them, they are dependent on the filter themselves. So which means that in a way E naught and E1 are kind of independent of each other. If you start imposing additional constraints, yes it is possible, but in the general case this is not satisfied. So because we made the claim that this is true in the general case. So in the general case, if you want to get aliasing cancellation, the only option that will be possible is this combination. So if you satisfy this, then T of Z becomes some scale factor, basically it will be 2 times C naught C1 and it will be equal to Z inverse or Z power minus N naught plus N1 plus 1, no 2 N naught 2 N1 because it is Z squared plus 2 N1 plus 1. Okay. So this is the overall delay. Now that it is very good from removing the magnitude distortion, but if I now go back and look at my H naught of Z, H naught of Z is C naught Z power minus 2 N naught plus C1 Z inverse Z power minus 2 N naught, or in other words it is C naught Z power minus 2 N naught plus C1 Z power minus 2 N1, this should be N1 2 N1 plus 1. Okay. It is a combination of two delays. H naught of Z, combination of two delays, you can choose those two delays to be at any location. So basically an impulse response that looks like this, some basically some combination of delays, and you cannot get very good filters with just a 2-tap filter, you cannot get very good attenuation. So yes, so this is going to be a highly restrictive case, this is not going to really satisfy. So yes, this is okay, but this is a very restrictive case, okay, very restrictive. It is a combination of two delays therefore, I cannot get very good filters to begin with. Of course, they will satisfy the magnitude constraint being cancelled completely. Okay, very restrictive. So, this is the final conclusion from our discussion. Of course, if you remember, we said that how about if you relate them to each other so that they can cancel, and that was an observation that was made. Yes, so we can look at an alternative. Instead of choosing them to be delays, I can of course choose E1 of z to be equal to 1 over E naught of z. Am I right? E1 of z is equal to 1 over E naught, or either way, because if you do this, it turns out the following: T of z will be equal to 2 times z inverse, which means you actually get perfect reconstruction. You have eliminated aliasing. With this, with one stroke we have eliminated both amplitude and phase distortion, because you were able to write the transfer function as a product of two terms, and if you force one of them to be the reciprocal inverse of the other, then you will actually cancel them, and then you will get a perfect reconstruction. So, if you remember, see, if I have, let us say, just 1 plus z inverse, that is a filter that. So, what will be the response of this? This is what it will look like, right. Basically, this is the filter response. Now, if I decimate this by a factor of 2, this by the way, this is pi by 2, I will get huge amount of aliasing, correct. I will get a very large amount of aliasing. Now, if I do not do any processing, I will be able to recombine and get it back, but the minute I do any quantization or something, then the reconstruction will be a mess, because a lot of aliasing has crept in. Now, that is where the problem lies. I should come up with a system where even if I have done some processing, I should be able to reconstruct with a fair amount of fidelity, right. So, that is why I do not want to introduce a lot of aliasing in the signals to begin with. Now, if I want to impose that, then this is not a good filter. I would rather have something which had like this. This would be a preferred one, because that will reduce the amount of aliasing, and then when I do the reconstruction process does a reasonably good job with that, right. So, that is why we are saying the combination of two delays is not is a very restrictive solution from the point of view of designing a filter bank that will handle a general class of filters, general class of applications. Okay, now let us come back to this option. Any difficulty with this? It becomes an IIR filter, right, because the minute you say that this is one of the polyphase components, that means even if E naught of z was a FIR transfer function, E1 of z becomes infinitely long, because 1 by this one. So, which means that this filter become IIR. So, we were actually interested in working with FIR filters. Okay. So, this is an indication that maybe if you relax that constraint that you want to have only FIR filters, maybe there is some interesting solutions that are possible. Okay, we make note of that. But this has another drawback. Any other drawback? One is IIR. Any other drawback? Stability, because I am not guaranteed stability. I may end up with something that is unstable. So, it is IIR plus stability, and I will put a question mark. There is no guarantee of stability. So, yes, I cannot do brute force way, though it gives me an indication that hey, maybe your constraint is too, you are already imposing too many constraints. You are asking it to be FIR, you want aliasing cancellation comes for free, because I know how to choose the filters. But you are asking for quadrature mirror symmetry, and you are satisfying this condition. Okay. So, now as I mentioned in the last class, we will go back and look at the transfer function. Look at the transfer function, it is T of z is equal to 1/2 of h naught of z f1 of z plus h1 of z, sorry, this should be f naught, f1 of z. This is my transfer function. Now, the thought process that goes about is that, okay, now magnitude distortion we tried to eliminate, we went so far, it seems to be a little bit complicated. We split it into polyphase components. We said that okay, maybe the indication is to go towards IIR. So now let us try the other side. Let us say that aliasing cancellation is done. I choose the aliasing cancellation. Quadrature mirror filters condition satisfied. Magnitude distortion I am going to allow. Okay, magnitude distortion allow. Magnitude distortion minimize. I am not trying to eliminate. So I am not going to ask you to make it into a all pass function. Minimize. And can I phase distortion eliminate? Phase distortion eliminate. Can I do this with FIR and FIR? Okay. So this is the we are basically approaching this problem from all possible, and it is a very good model for how you would do a research problem. You get the transfer function and then you say okay, I change this parameter, I change that, I combine, look at it, and but you may hit dead ends, and we kind of hit a dead end with trying to eliminate magnitude distortion. So for this we say that okay, we will go to the class of linear phase filters, and if you would recall from Oppenheim and Schaefer, ONS, I write it as OSB because there is a previous version which is Oppenheim, Schaefer and Buck. So if you have the later version, it is Oppenheim and Schaefer and Buck. Okay. In that you can find that there is a classification of filters that is given to us. The classification of filters is in the classification is in terms of the order and the symmetry. Okay, and let me just write it down. Type 1 is even order and even symmetry. Okay, and order is defined as if I have h of z equal to h naught plus last term is h of n minus h of n, h subscript n, z power minus n, n is the order, n plus 1 is the number of coefficients. Okay, the number of coefficients is one more than the filter order, and so the filter order that we are talking about is n, and if that is n is even, then it is called type 1. And then you have type 2, you have type 3 and type 4, type 3 and then type 4. Please go through and fill in all of the categories. What is of interest to us is the type 2 case. I will focus only on that. So type 2 is odd order and it is even symmetry. Okay. An example of type 2 would be h naught plus h1 z inverse plus h2 z minus 2 plus h2 z minus 3 plus h1 z minus 4 plus h naught z minus 5. Notice filter order is 5, the number of coefficients is 6, but because of symmetry you need to worry only about 3 of them, half the number are so this is the type of filter that we are interested in. Let me just write the expression for it and then leave it to you as an exercise for you to h naught e of j omega. If this is h naught e of j omega, and let me just make it plus dot plus h of n times z minus n, that is the general form. So h naught e of j omega in this case can be written as e power minus j omega n by 2 summation k equal to 1. This is not as important, so but if you have a doubt, please look it up in Oppenheim and Schaefer. This would be bk cosine omega k minus 1/2. Okay. What is important for us is that this is a real valued function. It may be positive or negative. Okay, because this is a sum of cosine terms that are getting added. Does not matter. So all the phase term is captured here. and there may be a plus pi if the real valued function turns out to be. So, we will call this as some real valued function h r e of j omega. Okay. So, very important, we can now write it as e power minus j omega n by 2 h r e of j omega. Okay. Now, please take this and substitute it into 1 with all of the symmetries that we have written down, and please verify the following result, that magnitude T e of j omega can be written as 1/2 of magnitude h naught e of j omega whole squared plus h1 e of j omega whole squared. Okay, that is magnitude response, and the phase response is e power minus j omega n. Okay. So, this is, you have to show this thing, please show this result, to show using 1 and 2. So, notice that the phase distortion has been removed, and now we have a condition on the magnitude distortion, and I know that h naught is h1 is the same as h naught e power j omega minus pi, that is the quadrature mirror symmetry. Okay. So, now this tells me also a way to actually satisfy the magnitude constraint also through a design process. So, I can design my filter h naught such that this is very close to a constant C, the magnitude squared response. And just a last point, what does that actually mean? If I have a filter like this, quadrature mirror filter, what the condition says is, take, if this is h naught, this is h1, take magnitude h naught e of j omega magnitude squared. So, basically square this, then square the second term h1 e of j omega magnitude squared and add them together. So, basically I will just draw it for the purposes of squaring. This is the squaring here, this is the squaring of this term here. What I get through the addition process is something that looks like this. I want something that is a constant. Okay. So, it is possible, but we have to design the filter h naught with slightly different constraints. What are those constraints? How do we design them? How do we get good filters to this is in the next class. Thank you.